I will review recent mathematical results in the field of aging of min-field spin glasses. Of course, I'm going to define all the words that appear on this first slide. So let me start. Yes, with the models. Okay, so given an integer n, I will denote by Vn, the n-dimensional discrete cube, minus 1, 1 to the n, and by sigma, a configuration, that is a vertex of the cube. This is a sequence of n spins. Min-field spin glass Hamiltonian on Vn is a centered Gaussian process, Hn, indexed by the configuration sigma of Vn. And as you can see, I have not defined just one Hamiltonian, but a whole sequence here, indexed by n. And since we'll later be interested in taking the limits as n goes to infinity, I shall construct the whole sequence on the same probability space, omega fp. This space is usually called the probability space of the random environment in mathematics. In physics terminology, I guess it's called the space of the disorder. We'll probably talk about the random environment here. So we're left to define the covariance structure of our Gaussian processes, and of course, different choices of the covariance will lead to different models. In the base-spin SK models, the covariance between sigma and eta is defined as n times the overlap between sigma and eta to the power p. So what I call the overlap is the quantity in the brackets, 1 minus 2 over n times the Hamming distance between sigma and eta. And the Hamming distance is defined as the number of coordinates or spins between the two configurations that disagree. So you see that if sigma is equal to eta, the distance is 0 and the overlap is 1. If on the opposite sigma is minus eta, this distance is maximum and equal to n and the overlap is minus 1. And for all other values of the distance, the overlap is in minus 1, 1. This model was first introduced with p here equal to 2 by Sharrington and Kirkpatrick, and they proposed it as an exactly solvable model for a min-field spin glass. It turned out that the model was by no means simple and not solvable either. What they had obtained was just a small part of the high temperature regime of the model, and it turned out to be very hard to solve. So Derrida had the idea to introduce the family of models with p larger than 2 as a family of models with weaker and hopefully simpler covariance structure. So the point is that when we take p larger and larger here, we see that the half-diagonal elements of the covariance matrix become smaller and smaller because it's strictly in minus 1, 1. And taking formally the limit as p goes to infinity, these half-diagonal elements drop out. And what we get is a diagonal covariance. The model that is defined in this way is called the random energy model. And this model is indeed solvable, but it is only a family of IID random variables. So indeed, it is perhaps an oversimplification because we lost a lot of the structure contained in the initial model. So finally, Derrida proposed that to simplify the covariance structure of the base-spin SK model, one should use an ultrametric distance instead of the Hamming distance and replace these powers here of the distance by increasing functions. And what we get is the family of generalized random energy models, the GREMs. So, and this family is also exactly solvable, and we know everything we want about it. These models remain in large part mysterious that we saw in the talk of Nicolas Kissler. So in this talk, I will mostly discuss the dynamics for the base-spin and the random energy model, basically because the GREM is still work on the way. So, okay. So just a few words about yeah. So in this talk, we will want to think of our Hamiltonians as random energy landscape. By this, I mean discrete random surfaces on the hypercube. So to each vertex of your hypercube, you attach a value, hn of sigma, of your Hamiltonian, and you think of this as a surface discrete on the hypercube. The statics of this model is now, the family of P-spin-SK models is partly understood, at least mathematically. The predictions made by Parisi via the symmetry braiding replica method have been now proven rigorously by Gayrard, Talagrand, and later by Pachenko. So this is what Nicolas Kissler explained to us the other day. But the problem is that this marvelous method that Parisi invented to find solutions, we don't know how to infer from these results any information on the geometric properties of the random environment. We don't know how to deduce what is the extremal process, the critical points, the level sets. Indeed, this is still very mysterious. So there are things that we know very well via this Parisi method, but most of the properties of these models are still unknown. I wanted to stress that the understanding of the dynamics was in fact an early motivation for the study of spin glasses, because it is believed and observed in part in laboratory experiment that these systems are never in equilibrium. And here I copied a sentence from the introduction of a paper by Pouchot, Cogliandolo, Courchan, and Mézard, who says that indeed they are not in equilibrium even on geological timescales. So the statics, of course, matters because it describes the equilibrium properties of the model, but the dynamics is, of course, a major problem to understand. Okay, so let me tell you now which dynamics we will be interested in. First of all, the equilibrium properties of the models are described by its Gibbs measure here. Gibbs measure G is the random measure that assigns to a configuration sigma on the hypercube the Boltzmann weight exponential minus beta h divided by a normalization. Beta here is the inverse of the temperature, and Z a normalization that makes this a probability mass. The dynamics we are interested in are Markov jump processes, xn, that evolve along the edges of the hypercube, and that jump from sigma to eta at a rate lambda n that is reversible with respect to Gibbs measure. So this means that the rates obey the detailed balance equation. This is if sigma and eta are nearest neighbors. The twiddle here means nearest neighbors, and there are 0 else. Okay, so that's a classical way to define dynamics. Then there is an alternative description of this dynamics in terms of its jump chain and holding times. The jump chain serves to describe the trajectories of the process. It is the discrete time Markov chain, Jn, that takes steps from sigma to eta with probability Pn, given by the ratio of the jump rate, lambda of sigma and eta, divided by this quantity here, which is the sum over all near eta prime, nearest neighbors of sigma, of the jump rates from sigma to eta. And I will call this quantity the sums lambda n of sigma. Then at each step of the jump chain here, the process xn waits an exponential time with this parameter, lambda n of jni. And if we condition on the trajectory of the jump chain, then the collection of holding times form a collection of independent exponential random variables. So this is an alternative construction of our process. Now, of course, we have several ways to choose rates that are reversible with respect to Gibbs measure. So which dynamics should we choose? The most widely used and best studied one so far is the random hopping dynamics the rates, lambda n, to jump from sigma to eta here are proportional to exponential plus beta h of sigma for all nearest neighbors sigma, eta of sigma. So we see that when it jumps, this dynamics chooses its next state uniformly from its nearest neighbors. So the jump chain is the simple random walk on the hypercube. And as a result, the mean holding time at a given site is the Boltzmann weight. Now, this feature that the jump chain is the simple random walk is not very satisfactory because in realistic dynamics, the trajectories should decrease the energy. And obviously, a simple random walk doesn't see the random energy landscape. So the archetype of a process that does have this property is metropolis dynamics, whose jump rate are now proportional to the exponential of minus beta times the difference between the energy of the landing point, eta, minus the energy of the starting point. So this dynamics, as we'll see later, has good properties, physical properties. So in this talk, I will discuss these two dynamics when the Hamiltonian is either the Pace-Mineski model or the random energy model. And what we are interested in is in the low temperature. I'm sorry, I'm listening to you at the same time. So we are interested in the low temperature relaxation dynamics. So away from equilibrium, the out of equilibrium dynamics. And in a particular pattern of behavior that is supposed to characterize the out of equilibrium dynamics in min-field spin glasses in general and in spin glasses at large, which is called aging. Okay, so to quantify this phenomenon called aging, one uses a time-time correlation function, Cn. This is a function of two times that are represented here on this picture. So this is the time axis. Time is measured on scale Cn. The process is started at 0 in some initial condition mu n. Then the time-time correlation function here serves to measure how much the process at time tw plus t remembers its state at time tw. So tw is an age, and t is a duration. And we measure a correlation between the state of the process at these two times. So there are several ways to define a correlation function, but in this talk, I will define Cn as the probability that the distance between the state of the process at time tw and its state at time t is smaller than some small epsilon when time is measured on scale Cn. And this distance can be a distance of your choice, any distance you want. Now we'll say that aging occurs if, as n tends to infinity, the time-time correlation function has a well-defined limit, C infinity. But this limit no longer is a two-point function, but only depends on the ratio of t to tw. And this limiting function here looks like this. When t is much smaller than tw, this ratio here is small, and here the correlation function goes to 1. While when tw becomes larger than t, the correlation function goes to 0. So that's normal, the system must decorrelate. But what we see is that process age tw here needs to wait a time t of order tw in order to decorrelate. So the older the process is, the longer it takes for it to decorrelate. And this is the particular relaxation pattern that is called aging. There are other types of limits that may be relevant in the study of aging. I wrote another one here that consists in first sending the size of the system to infinity and then taking times to 0 simultaneously keeping the ratio here, T to W, fixed and equal to some rho. Other scaling relations between T and TW are also possible. There is, in the physics literature, you can see a whole zoology of scalings. Yes, you will see y to 0 in the next slide. Yes, it's really to 0. You will see on the next slide. Shortly, very shortly. You will understand it immediately. So I just want to conclude this slide. So there are lots of scaling relations between T and TW that appear in the physics literature. So what one should retain is that asymptotically, aging occurs when this time correlation function is not time translation invariance. That's a generic definition. Okay, now I want to tell you what we know about aging in the simplest dynamics, the random hopping dynamics of the simplest model, the random energy model. So this is the diagram of its dynamical phases as a function of the temperature. The inverse temperature is here, beta, and the time scale. Time scale is here, gamma, measured on a logarithmic scale. So in fact, the time scale, Cn, is a function of gamma and is defined as, well, by this big blue formula here. It is the exponential of n beta gamma minus logarithmic correction plus a constant. So we see that here we take 1 over beta n log Cn, okay? So when we fix a value of beta and go up here along the vertical axis, we increase the time scale. So formally, the statics should be here on the horizontal axis. So let me briefly recall that there exists a static critical inverse temperature, beta star equals to square root 2 log 2, such that for beta larger than beta star, so at low temperature, Gibbs measure converges weakly to a Poisson-Dirichlet random measure. The support of the measure is carried by an infinite countable sequence of configurations called the ground states, and each of them has a strictly positive mass. On the contrary, when beta is smaller than beta star, no single configuration carries a positive Gibbs mass in the limit, almost surely, and here the Gibbs measure essentially resembles a uniform measure. So we see that there are two important lines here on this picture, the line beta equals beta star and gamma equals beta star. This vertical line here, as I have just said, separates the low temperature region to the right from the, from the high temperature region to the left. The horizontal line here, when gamma equals beta, defines the shortest time scale such that the process has time to find its ground state. So this, for when gamma equals beta star, Cn of beta star is the shortest time scale on which the dynamics has time to see the configurations that are in the support of Gibbs measure. If you look at a slightly shorter time scale, the dynamics never has time to find the ground state configurations. If you look at a slightly larger time scale, it will find them very quickly, and then it becomes very quickly stationary, whatever the initial definition. So this defines here this stationary phase that I call 2. Then below this line, everything will strongly depend on the choice of your initial distribution. And I will start from a uniform distribution because that's what is done in physics. It mimics a deep quench. So we still have two parts in this remaining picture. So we have a red line here defined by the diagonal gamma equals beta up to beta star, and then by this plateau. Strictly below this blue line, in the entire region below it, the process is aging, namely the, yes? Mm-hmm. Yes. 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 Yeah, so I choose my time scale, and I look at my correlation function at this time scale. Yes. It's a parameter. Yes. 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 Absolutely. Exactly. Yes. So this is what I'm trying to explain, but so in this complicated picture here that I tried to make simple, but so in this region that I call 3 below the red line, the 2-time correlation function of the previous slide for almost any distance you want to pick converges to a function that is a function of a ratio of TW to T. So it is aging. This function here, ASL of gamma over beta, is the probability distribution function of the generalized arc-sine law distribution with a parameter gamma over beta. So I didn't write it down because it was taking too much space. Yes? So yes, it is the same as that predicted by Bouchot for the trap model. Yes. Yes, it's in fact, if you so Bouchot introduced these trap models that are Markov jump process on complete graphs. So these are very simple little graphs, and it did that thinking of constructing a dynamics on the ground states. So he said, okay, this model is too complicated. Let me just pick the ground state and construct the dynamics directly on it. So he made the ground state finite, I mean finitely many, and then took a limit as the number goes to infinity. So it is a ad hoc reduction of this dynamics to a simpler dynamics, so a kind of mapping of this dynamics on a simpler state space, smaller state space, but it is an ad hoc construction. So what we did is that we proved, well, it's if I'm ever finish this slide, you will know who proved what. But yes, so this is what Bouchot predicted with the trap model. So this arc-sine law distribution function, I didn't write down its definition, but it is the function that was a correlation function that you saw on the previous picture. Should I make it a little drawing again? So okay, so the slope here and the slope here, they depend on the parameter gamma over beta. And in this picture, gamma over beta is strictly between 0 and 1. If you take this ratio larger than 1, then the function has a different shape. Yes, this is the time scale. Yes, yes. Yes, yes, exactly. Exactly. Okay, so we still have to describe these two transition lines. So when gamma equals beta star, the time rescaled process x on time scale Cn of beta star converges to an ergodic process, which is a k process. And I won't define it because it's extremely technical, so I think it's just better forget it. But then here is the explanation to your question, Jan. If you start from this ergodic, so here on this line, since the process is exactly ergodic, this limiting process here is a jump process on the infinite sequence of ground states. It's not aging. Here, aging is interrupted. But if you take this time, so this 2 time here, is if you take here this TW and TW plus T, if you take them to 0, so you take a limit, so this Cn is what it is, and you take a limit independent of n of tw and t small. So you just look at the very last time scale before stationarity. You look to the stationarity from below, and this is why here you're taking this limit, you re-enter the aging region. If on the contrary you were taking a limit of this times here to infinity, then you will fall into the ergodic region, and then the two-time correlation function becomes time translation invariant, and aging is over. This transition line here is the low temperature liquid to solid glass transition. Okay. Then there is another transition line here, which is a transition from a high temperature, small time scale stationary regime to the aging regime. Now, we see that on this line, here the right-hand side looks like an aging function, but actually we don't have aging because we have a square root n here in front. So this means that the two-time correlation function begins to decay when it crosses this line to then go to 0 on the other side. And indeed, this was quite a surprise to us to find this, because this disagrees with Bouchot's finding that predicted with the simple complete graph model, where they have this result without this square root n there, and this square root n really comes from the graph. Being on the hypercube, a very high dimensional graph, is something different than being on a simple complete graph. Yes. Yes. So, so I have summarized here the works of several persons and many years of work. It started with my joint work with Gérard Benahous and Antoine Bouvier, where we obtained this limit of aging on the last time scale before stationarity. Then Benahous and Czerny discovered that aging was also present on some smaller time scale region of the plane. I extended it to the full aging region called 3 here, including this transition line. And this last transition line is a recent result with Lisa Hartung. I only cited this paper here for those who are interested because it summarizes all the other works, and one can find all references to all other works in there. Yes, exactly. Yes. So what about the p-spin? Yes, I just should still mention that this result is an almost sure result in the random environment, almost all the way up to the transition line, where it comes here to converge in low only. Okay, so for the p-spin SK model, so the time scale is the same as before, same definition. The initial distribution is the same as before, and the definition of beta star as well. So we see that this blue line here, that is the diagonal up to beta star and this plateau, describes the region called 3 on the previous slide. It is the aging region of the random hopping dynamics of the random energy model. And what we can prove is that in a smaller region, the two-time correlation function of the p-spin SK model has the same aging behavior. So the theorem states that there exists a strictly increasing function, gamma c of p, that increases to beta star as p goes to infinity, such that for all values of p larger than or equal to 3, and in the region here delimited by the diagonal, beta equals to gamma up to gamma c of p, and then the plateau from gamma c of p on. In this, below this region, strictly below it, the two-time correlation function of the p-spin converges to this Harksine law distribution function. P almost surely in the random environment for all p strictly larger than 4, and in p probability only if p is equal to 3 or to 4. This result was first obtained by Benarous and Czerny, but in low. This means that they take an average here over the random environment, and our result is an almost sure result. So we see that this function, gamma p here, increases, and it increases up to beta star as p goes to infinity. So this red delimited, this region delimited by the red line, it will grow up to coincide with the blue line. So this is natural. The model should converge to the RAM. So in a sense, yes. Yes, so indeed, it is a bit the when p equals 2, lots of things collapses in mathematics analysis of this model, and the fact is that the correlations are really stronger. So I do know things about the SK model, but not on timescale that grow as fast as exponential in n. They have. Yes, this just means that the correlation functions are too hard for me to understand. It doesn't mean that there's no aging of this form. I would be surprised that this kind of aging appears, because if it did appear, it's that there would be something simpler enough in the correlation so for me to see it. And it just doesn't happen. So the p equals 2 is a really harder model than all the others. What I should say here is that so morally this the reason why it's sort of surprising that we can get such a strong result over such a large region of the plane for the P-spin SK model. We should think of this as being a situation that is akin to the one level of replica symmetry breaking. There is enough independence still to be able to understand the model. And in this region here, well, we just don't know what happens. Correlations become too strong for us to understand. But you know, the predictions is that the P-spin SK model jumps from one RSB situation to an infinite RSB situation, so there's nothing simple in between. Okay, I just for the sake of completeness put on the picture what we know about stationarity. So here the process is in a stationary phase of type 1 by analogy with the previous slide. It is a stationary for a particular initial distribution, which is a uniform distribution. I don't know the result for all possible initial distributions. And recently, Benarous and Jagannath proved a lower bound in the mixing time, which I couldn't put on the picture because it was not explicit enough to understand, but it's somewhere here, in a sense. There are precise analytic expressions for these quantities, beta C of p's and gamma C of p's, but I did not write them down. So the question now is this arc-sine low aging regime that arises both in the RAM and P-spin SK model, is it a property of this particularly simple dynamics that we chose, or is it something that really follows from the properties of the environment? It could be that the random hopping dynamic is such a simple dynamic that it is an artifact of this choice. And in particular, would the result be the same for metropolis dynamics? So we now have the answer for the random energy model. And the answer is that, yes, indeed, aging in metropolis dynamics of the random energy model is the same as aging in the random hopping dynamics of that model. So what one can prove now is that this two-time correlation function converges as before to the arc-sine low distribution function, almost surely in the environment, and in the entire aging region we found before, but not exactly up to the ergodic time scale here. So gamma must be smaller than beta, that's this diagonal line, and it must be smaller than beta star, so smaller than this, times 1 minus this small constant here, times square root log n over n. So this is, of course, extremely small compared to 1, so you will think that it does not matter. Yes? 5? Okay. But if you plug here this into the definition of the timescale, then you see that you get a prefactor in front of your ergodic timescale that is that is still something going to 0. So you're not yet reached your ergodic timescale. So this is so this means that the whole picture is the same, but we don't know anything about, or don't yet know anything about these transition lines. This transition line here is not a simple problem, so there are teams of physicists working on it right now. Enzo Marinari in Rome and his team, and Giulio Biroli with his team. And so they are trying to understand numerical simulations about this, because this glass transition line is what people are really interested in. And then what they say is that they cannot manage to do numerical simulations because as you get close to this transition line, the size effect corrections that you have, they start to diverge. And if they diverge, it must take larger systems. But your time scales is exponential beta n, so you have to do computations on things that diverge much too fast. So they just can't manage to do that. And since on top of it you must take beta small, then you have to work on timescales that are exponential beta gamma n, and everything is going to infinity, and so they just can't do it. So what happens here on this line is still an open problem, both from the physics point of view, I guess, and from the mathematics point of view. So you said I had 5 minutes? Yes. But I don't know, perhaps I'll stop here because I don't think I have really time to start to describe techniques. So one slide. Okay. What can make aging occur? So when you ask yourself this question, then you go back to the jump chain and holding time description of your process, and you form a clock process. The clock, SNK, is the total time spent by the jump chain AN along its trajectory. So it is the sum from I equals 1 to k of the mean holding times at side j and I times the little exponentials. The mean holding times are exponentials. Now if you inverse this clock and use it to time change your jump chain, you get back your process. This is the classical construction of a Markov process. Now this clearly suggests that the clock should play some role in the slowdown of your time-time decorrelation. And indeed, in all examples where aging has been proved to occur so fast, the time decorrelation comes from an anomalous behavior of this process. What happens is that we can find sequences of timescales, AN here and CN, that's our timescale, such that this clock converges as n goes to infinity, but the limit is not trivial. It's not a law of large number type of limit, it's something else. And I will tell you what this something else is without turning slide. This something else are Levy processes.